Okay, thanks. Cannot turn down people's choice. So, well, I will be continuing of what I discussed yesterday, but I want to explain maybe a little bit more intuitions. And so the plan is to I will discuss the design of the procedure, the linear estimator, and why it looks like design a filter.
Yihong,
Up here? Okay. So the linear estimator and why it looks like a filter design. And then I want to discuss the impossibility result and what is the bad distribution. What does the worst instance on the ensemble of instance looks like? What's the bad distribution? And I will discuss some extensions, some limitations, and other related open problems. I don't know if they are open or not. So. Right, so I want to so let's get started. The setup is I have n samples, and I want to know how large is the support. The support size, not the set, is number of non-zeros and number of non-zero mass.
You want black?
Okay.
Another one if that doesn't work.
Right. Okay, and now we want to ask what's the minimum sample you need, for which we need to constrain the distribution to have some lower bound on the minimum mass. I'll discuss this later, the assumption, but what I know is P belongs to a set of distributions, which is all distributions which each mass is either 0 or bigger than something. I just put okay, right? So, right, and I define n star of n and k and epsilon, which is the minimum sample size, such that you can find estimator, which is belong to the truth plus minus k of epsilon with high probability. I can put constant probability with probability at least 90%, right? For any p belong to this set. So this is the statistical fundamental limit, if you wish, and the goal is to characterize this and find a good procedure to attain it, right? So I showed you that the result is subly.
Yeah, it's very thin.
Oh. This is better. Right. Yeah. Okay. This is better. So it's sublinear in K indeed, and the dependence on the how accurate your estimate is logarithmic instead of polynomial, which is what the previous result showed. Okay. Okay. So I want to discuss something about. So there are a lot of procedures along these lines. So there are linear estimators and also nonlinear estimators. Linear in what? In the sufficient statistics, the fingerprint, which is the histogram of the histogram. So this is the number of items appeared exactly j times, right? And this is the number of appearances of the ith guy. So this is the histogram. So linear estimators meaning I'm going to design some f that applies to every histogram. Or equivalently, this is a linear combination of some appropriately chosen coefficients applies to the fingerprint. So the Sing estimator is just sum everything up, and this is what you estimate is what you see. And also there are other good Toolman with oscillating coefficients, and also F1 T-stat about design different coefficients, right? I'll focus on this, but I think it's fair to discuss other nonlinear estimators of not of this form, just briefly. And there is, for example, a pattern maximum likelihood that Olitsky et al. Designed, which also you can use it to estimate the support. And also there are linear programming based method that I will not discuss. And there are also, let's say, coverage based. What does it mean? So coverage based meaning, first, I want to estimate the following quantity, which is the total probability of everything I have observed, which is a summation of pi of everything that appeared in my data. Right? So this is some probability, and 1 minus c is the probability that next is new. Right? Conditioning all my data right now. Okay, so this is usually called coverage. And I know my the total number of observed samples is underestimate, so I should inflate it a little bit, right? So the way to do it is, if I have a good estimate for the coverage, I just blow it up. By that, it will give me some reasonable estimate, right? It will be less underbiased. But one of the ways to do this is to do good Turing. And then in this way, it's some nonlinear function of the fingerprint. And there are also, so this is another one.
But you don't know the probabilities either, right? So.
Oh yeah, so I said put some estimate here. For example, good Turing. For example, good Turing. This is 1 minus h1 of n, right? So it's some heuristics. But the idea is that you want to inflate it. And also there is a maximum likelihood estimate. Of course, now you need to say what's the family of distributions you're looking at. And for example, you can do uniform distribution. That will be one family of distribution parameterized by exactly the size of the support. And you can find the equation for the maximum likelihood, and it has been analyzed. It works pretty well in the uniform case. So pattern, maximum likelihood, and maximum, and this good Turing also works very well. Provably, actually, in a special case where the distribution is flat. But you will see that the worst case, the bad instance of distributions, are actually very, very non-flat. Okay, anyways. So I will discuss a little bit about the design of coefficient like this. Right? So this is the upper bound. But intuitively, what I will do is, I say I will do the following. If you think about it, and I want to know this quantity, so just in terms of bias, I want the expectation of this to resemble this function, right? So what I do is the following. Look at the difference. Well, the first thing I said is I have a first design principle, which is if something doesn't appear, I say 0. Right? Okay, so if the corresponding mass is 0, and then it won't appear, and therefore I'm also 0. Therefore, I can put the indicator outside. Right? 0. And I also know, by assumption, if it is not non-zero, then it's at least 1 over k. Right? Okay. So I do this, right? And also I have another design principle, which if something appeared for many, many times, I just add 1. So another design is, if it is bigger than 1, if it is bigger than some threshold, I say, okay, that's in the alphabet. So in other words, this also further simplifies to the indicator where it appeared less than L, because it's bigger than I'm exactly good. Now, here's another simplification. With high probability, the following is going to happen. If something out of n samples appeared at most L times, the corresponding mass will not be bigger than 2L over n with high probability, right? So if L is not sufficiently small, so L is roughly log of n, log of k. So with high probability, I'm very confident that whenever something appeared no more than L, the mass is at most 2L over n. Okay, now I can take expectation on both sides. And this will become expectation of this quantity. So here is the a little bit of variations. I can either do Poisson sampling or not. I can even without doing it. So let's do it. So the Poisson sampling meaning, instead of n samples, I draw Poisson n samples, and it's just stochastic relaxation, but it doesn't appear, it doesn't hurt me much. And you will see it's still not important at this stage. So what this is f of I minus 1, I factorial, e to the minus n, p of j, n of p of j, to the n. I from 1 to L. And then there's these indicators of the probabilities belong to this little interval, 1 over n, L over 2n. Right, okay, now you see that this is nothing more than e to the minus n of pj times some polynomial in p of j. So what I really want is this guy to look like the following behavior. So I have one constraint, is that the polynomial has to pass through minus 1 as 0, because this is minus 1. So the picture is the following. This is 0, this is minus 1. So whatever the polynomial I pick has to pass through here. And this is my little interval, 1 over k. I mean, if you view this as a variable, and this is 1 over n, and this is 2 of L, and I have to pass through here, and I want to have minimum oscillation over this period, right? So this looks exactly what you were doing if you design a finite order filters, and the best design is Chebyshev, actually. So this is the maximum loss I suffer, which is roughly e to the square root of n over. And this is precisely degree L Chebyshev polynomial, shifted and scaled. And the coefficients are readily available if you compute that. Right? So this is very much the idea here. And just give you a concrete example. If you have, let's say, if you have 1 million items, and if you have, let's say, 0.2 million samples, what does the estimator looks like? The estimators looks like the following. 7, H0, if something appeared once, I say there are 7 more times that, minus 25, H2, and go on and so forth. And this is 75, H3, minus something. So this is the oscillation part. And starting from 12, 13, 14, and so on and so forth, the signal to noise ratio is very good, so I can just say they are in the alphabet, right? So this is the flat part, and the degree here is 11, right? So this is what I implemented on some data, but roughly this is what it looks like. Yes, please. Yeah.
This would also work if you are interested in counting the number of elements.
Right, in some intervals, yes. Absolutely. So so instead of a low pass filters, you design something that is like that, right?
Do we want that assumption on PK in the sense that can we just say that we don't care what P is, we just want to count the number of elements with probability greater than?
Actually, that won't work. So that's what Ramon suggested, but I'll come back to that later. It's you have to be careful with how do you define the problem.
What does the degree of the polynomial depend on?
A log of, you can put log n here.
Log of the sample size.
Yeah, so if you have 1 million samples, this is roughly 10 or 9 or. Yeah. Right. So I'll address your question now. Actually, so I think so Ramon suggested yesterday is instead of estimating the total non-zeros and imposing the constraint that is bigger than something, let me just estimate the probability of the heavy hitters bigger than that, right? And I want to, so let's call it R of B. And I want to impose no constraint on the distributions, and I only care about the B guys. But I mean, it's very easy to see that this won't work because consider 2 instances of 1 over k. It's completely uniform. And let me put a 0 here. And Q is 1 over k minus epsilon. I put k epsilon here. And I put epsilon to do, I don't know, 2 to the minus n. Right? So you won't distinguish these two distributions if you collect n samples. But what is r for this? It is k. For this is 0. Yes? So it won't. So just it's essentially in this case you can only do one side inference. If you don't, you only can say, okay, I give you. You can only estimate. Well, maybe the support is at least how big, right? And you want to push that upper bound as aggressively as possible because you can always be very conservative and do the usual plug-in, but you want to essentially. This is the idea. I won't have much time, I think. Where's the chair? 5? Okay. So let me explain to you the main idea of the lower bound and what does it look like, the bad distributions. Right. So you want to construct, actually, you simply want to solve the following problem. In fact, there's two hypothesis testing. One is SP is less than something, S0, and SP is bigger than S1. So you want to, of course, maximize this to the point that with n samples, you won't be able to distinguish, right? So it's a composite hypothesis testing. So you need to design some good convex combinations on these two hypotheses so that their convex combination becomes almost indistinguishable. But I want to just say the main idea of designing these distributions which are random. So think about the following idea. So if I have a random variable u, which is drawn through some law of mu, and u has the property that has one unit mean and positive, I can generate distributions of the following form. I have k copies of them, and I say this is my distribution. Of course, it won't normalize, right? It is not on the. So if this is a probability simplex, this is not going to be on the probability simplex, but it's only within a little bit of fluctuations, because the sum of the probabilities is 1 with law of large numbers, plus minus standard deviation of u divided by root k, right? So u will not be fixed. U will grow with the sample size and everything. But as long as you make sure this is like log k, or even if, k to the 1/3, you can ensure you are in a small tube along the probability simplex, so you can effectively treat this as probability distribution. So let's not discuss that. But I want to give you some examples of this form. So examples. U is constant. In other words, is drawn through delta of 1. What does it look like? P is exactly uniform distributions, right? Yes? Okay, so another example. U takes two values, 0 or 2, with probability 1/2. So if you draw the corresponding distribution, what does it look like? It looks like very much like uniform distribution on half of the alphabet, and the support is uniformly peaked, right? So this is roughly the symmetrized version of this type of things. I can also give you, let's say, uniformly chosen from the interval 0 to 2. Then if you draw n k copies of this, you will get a distribution where all the probabilities are going to be different, right? But anyway, so the role of u plays the shape of the histogram of this distribution. And the goal is to design something that makes them design two shapes that generate data with indistinguishable the histogram. But I don't have time to go into that, but I just want to give you the idea of what does it look like. So at the end of the day, the distributions will look like the following. So this is P. And this is another P prime. So these are the two nemesis that. And so these are, think about, these are drawn from U, and this is drawn from U prime. And U prime actually only takes log values. This is not important for the proof, but I want to just give you some intuitions. And So you have, U1 over K, and this is what the probability that U equal to U1 times K. So a fraction of the alphabet takes these values, fraction of this takes this, and the biggest mass and the smallest mass actually differs a lot. So in the special case of the sublinear regime K over log K, I have around log K samples, and the ratio of the biggest mass and the smallest mass is around log square. So they are very ununiform, and in this case, you can show that the construction that yield, this is roughly, I will just put some constant 0.5 K, and this is 0.6. So they are constant fraction of the alphabet is populated, and somehow you pick these things in such a way that you match the moments, and they generate the data that is indistinguishable. But these are the rough ideas. Okay, yeah, all right. I'll just stop here, and we can discuss about other open problems later.